Welcome back. This is our first video of section 5.6. Today we're going to be dealing with applications and models of exponential growth and decay. So applications just basically means story problems. So we will be dealing with story problems and making regressions for data sets in this section. So if we look at our first one, we're going to be talking about exponential and logistic growth. That's a new type of growth that we'll get into in a second. In general, we can use the following model for population growth. It says P of t, which is population at time t, where we have the initial population, P sub 0, e raised to the kt, where k is the exponential growth rate. So how fast are things growing by? And this is the general form that we can always use. So let's go ahead and look at example 1. It says a sample of bacterial culture initially contains 50 E. coli cells. The exponential growth rate for E. coli under optimal conditions is 4% per minute. So 0.04 is our exponential growth rate. That's K. So that equals K. A says, presuming optimal growth, how many bacteria will there be in 1 hour? We don't need to say bacterial, typo. Will there be 1 hour later? Now I want you to understand that our exponential growth is in 4% per minute. So if we have an hour, we need to think of this as 60 minutes. That's very important that you look at your units when you are looking at a story problem. So if this is our time is 60. Our initial amount of bacteria is 50 cells, and we already said that our K value is 0.04, and now we know our T value is 60, because 60 minutes. So we can just go ahead and plug this into the formula. P of t equals P sub 0 e to the kt. So if our time is 60, we're going to do P of 60 equals our initial amount of bacteria, 50, e to the 0.04 times 60. So you can go ahead and just plug that into your calculator all at once, and when you do, you get 551.158. And when you get a decimal like this, especially with a story problem, you want to go back to see if it makes sense. The question is how many bacteria? And we can't have a decimal part of bacteria, so we're going to say it's 551 bacteria. B says, how many bacteria are in the culture after 3 hours? So remember, we're still in hours, so we take 3 times 60. Okay, so if we have 3 hours, T equals 180. So we're just going to switch out 60 for 180, so this is P 180 equals 50 e to 0.04 times 180. And that gives us 66,971.53. So I'm going to say 66,972 bacteria. In question C, it says, how long until there are 1 million bacteria present in this culture? So we're asking for how long. So that means T is question mark. We're trying to find out. And this is the amount of bacteria present at P of t. So we know P of t equals 1 million. P naught is still 50. K equals 0.04. And that T is question mark, which we've already talked about. So let's plug everything in. 1 million is 50 e to 0.04 t. So let's first get rid of the 50. So we divide both sides by 50. And we get 20,000 equals e to the 0.04 t. If I want to bring down the t, the way we do that is by taking the natural log of both sides. So I'm going to say the natural log of 20,000 equals 0.04 t times the natural log of e. And you guys know the natural log of e is 1. So really, that's not even there. So then we're just going to divide this by 0.04. 0.04. I just think it's easier to do that instead of actually finding what the natural log is and having to approximate it. So then what I get is 247.58 minutes. Okay? And while we are talking minutes isn't really super helpful. If you noticed in A and B, they kept saying hours. So we're going to divide this by 60 minutes to get hours. So what we end up getting is T equals 4.13 hours. And it does make sense to have a decimal when you're dealing with hours because that's a continuous measurement, not like one bacteria that you can't really have part of a bacteria. So that's why I kept decimals for time but didn't keep it for my bacteria. Let's go ahead and look at example 2. Of course, I just got rid of some of the words, so let's see. It says continuously compounded interest follows an exponential growth function. You invest $2,000, so right there that's our P naught, in a particular account in which the interest is compounded continuously. Okay. It says, what interest rate do you require to have $2,500 in 5 years? So what we don't know is K. We know K equals question mark because that's our interest rate or the exponential growth rate. We do know that P of T is 2,500. And we know that time is 5 years. So we just have to solve for K. So plugging this into our function, we know 2,500 equals 2,000. That was our initial investment. E to the K times 5. Okay, so now we're just going to solve for K. So we're going to divide by 2,000. And when we do that, we get 1.25. So I'm going to leave it because it's a nice, pretty one. 1.25 equals e to the 5k. And then what we want to do here is we want to take the natural log of both sides. So I have the natural log of 1.25 equals 5k, because I brought that down in front, times the natural log of e, which we've talked about, that equals 1. So we can really just think of it as not being there. So now I'm going to divide both sides by 5. And when I divide by 5, I end up with 0.0446 equals k. So we can say about 4.5% interest. That's the interest rate we need to get to make $500 in 5 years. B, using the same rate, how long will it take to double your initial investment? Well, our initial investment is $2,000. So what's double that? 4,000. Good. So we're going to use this 4.5%, but now we don't know T. So 4,000 equals 2,000. Okay, sorry about that cough. I have a cold that I'm trying to get over right now. But I apologize for coughing in your ears. Okay, so if we're using our same interest rate, this is e to the 0.045 t. So we're going to solve it. Divide by 2,000. Divide by 2,000. 2 equals e to the 0.045 t. We're going to take the natural log of both sides. We get the natural log of 2 equals 0.045 t. Natural log of e, which you know is 1. So now we're going to divide that by 0.045. And when we do that, we get 15.4 years. So T equals 15.4 years. So that's how long it's going to take to double the investment. So what I want you to notice is when we take our doubling, no matter what, when we take that ratio, we should always get 2 because you're taking double your investment. So there's actually a little shortcut that you can do if you know that you are doubling. So the growth rate in doubling time. So we should know that KT, which is the 0.045 times T, equals the natural log of 2. That's one way to think about it. If you're looking for K, or if you're looking for T, this is the formula that you can use. And since this is growth, we know that K would be positive because it's obviously getting larger, so K has to be positive. Okay, let's talk about a different type of function that you've probably never heard of before. However, you might have seen the graph. It's called a logistic function. And a logistic function is the function that's used when we have a limited growth. In other words, it grows, but there's something that's holding that growth back, whether it's a limited amount of food or space or, just resources in general. So we use the logistic curve whenever we have a limited growth. And so they model the exponential growth, but then there is an asymptotic. Asymptotic means you have an asymptote upper limit. Here's our crazy function. And so it has the limited value A. So A is your asymptote. Okay, so the number on top is actually the number of the asymptote. It's also called the carrying capacity. So it's the maximum amount that a population can grow to. So the function approaches but never actually reaches. And so the shape is referred to as an S-curve. So when you see this type of growth, just like exponential, it starts growing quickly, but then we see it slowing down and becoming almost horizontal. So that's why they say it's an S-curve. So in example 3, it says, the bald eagle was nearing extinction in the early 1960s. As a result, it was placed on the endangered species list. Efforts to protect the eagle, including restoration of habitat, banning harmful pesticides, and protections of nests, have proven quite successful, as displayed in the chart. It says, create a scatter plot of these data on your calculator. What does it look like, and how does it compare to the standard exponential growth curve? Okay, so we never ever want to use 1963. If they don't tell us where to start, we're going to just start with this being 0. So that would make 1974 11. Then we have 1924. Wait, does it tell us? Oh, it says right here, sorry, after 1962. Oh, I apologize, I'm sorry. Let's erase that. So if 1962 is year 0, I knew there was somewhere. That means this is 1, 12, 19, 24, 28, 32, 38, and 43. So those are the values we're actually going to be plugging in. So let's go ahead and look at our calculators. So let me pull my calculator up. Gotta turn it on. Okay, we're going to go to Stat. If you haven't got your calculator out yet, go ahead and get it out because I don't know how often you have done regressions. So Stat, and then Edit. And if you have anything in your L1, you're going to arrow up and hit Clear and arrow down. And then do the same thing in L2. Highlight L2, hit Clear, not delete, Clear, and then arrow down. And it will delete everything that's in your L1 and L2. So in our L1, we're going to put 1, 12, 19, 24, 28, oops, 24, enter, 28, enter, 32, 38, 43. And then 487, 48. Okay, so now that you have all of that in your calculator, to do an exponential regression, we are going to hit, we want to graph this. So I'll start the next video with graphing this. I will see you in